So this chapter is going to be called, if you look it up, it's chapter 10, and your book is going to call it Chemical Quantities. So quantity, what does that mean? How many or how much, right? It could be how many if you're counting pieces. It could be how much if you're weighing stuff. Does that make sense? Okay. And because it's the central idea of what we're going to do, and I would not call this chapter chemical quantities, because that's what we're going to figure out. We're going to figure out how much about chemicals, how much there is, how much it will make. Okay, but if I was going to call this chapter anything, I'd call it Our Friend the Mole. We're bringing back an old friend. He's coming to visit us. He's got a star-shaped nose. Or is he coming to spy on us? Neither one of those kinds of moles. Okay, we've talked about moles last semester. Okay. Anybody remember what a mole was? It's not weight. It's about amount, but it's not weight. It's not a formula. Okay. A mole was defined like this. And the key word of that is right after the definitive article. After that, it says the number. The mole is a number. Just like dozen is a number. Dozen means 12. Mole means a much bigger number than 12. The number of carbon atoms in exactly 12 grams of carbon-12. That was our definition of a mole. And the reason why we need moles is because of the answer to the Bell-work question. Why do the coefficients have to be whole numbers? What'd you think? Why'd you put down the coefficients had to be whole numbers? You can't have fraction of an atom. You can't have fraction of a molecule, right? Even H2O is not an atom. It's got parts, but you can't have half of an H2O. Right? Doesn't make any sense. So those balanced equations are about particles, right? So it's got to react one particle at a time. So if I want to talk about how much it's making, I have to count the particles. So why don't I just work in atoms and molecules? Because there's a lot of them. Okay? A mole is a bigger number than 12. A mole is 6.022 times 10 to the 23rd. So that's 6.02. And I'm going to move that 23 times. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Give you an idea of how big that number is. Okay, so this right here is thousands, millions, 1, 2, 3, billions, trillions. Okay, so right here would be 100 trillion. And we still got millions of those to go. This is a big number. Are we ever going to be able to count it? Nah. But if you did try to count, if you started at the beginning of the universe and started counting 1 every second, you'd be less than 0.1% of the way through this number. So you wouldn't even be 1/1000th of the way there yet. So there's been less than 1/1000th of a mole of seconds in the history of the universe. It's a big number. Okay? But it's just a number. Just like a dozen is 12, a mole is that number. That number is given a name. It's called Avogadro's number. Named after an Italian scientist whose last name was Avogadro. And he was the one who figured out it was important to count how many pieces there were. That to understand reactions, you had to count the pieces. So that's why they gave that name to him. Because he was the one that said, ooh, the number is the important part. Okay? So there's Avogadro's number in a mole. There's avocado's number in a guacamole. Okay, so is counting an option? No, counting's not an option. So in order to get that number of atoms, we're going to use something called molar mass. And it is the mass of a mole. The molar mass. We studied molar mass before. We said it was the decimal number on the periodic table. Fact is, we use this to count atoms. We did some conversion factors where you had so many grams of sodium, you could figure out how many moles that was and figure out how many atoms it was. That's what we used moles for in the past. That's what we're going to use them for again today, this unit, is to count pieces. So if I look up carbon on the periodic table, it says 12.01. Okay? That means 12.01 grams of carbon is 1 mole of carbon. So if I had 12.01 grams of carbon, I would have 6.02 times 10 to the 23rd carbon atoms. And this is what we did with it before. If I had 6.5 grams of carbon, this is what we did before. We said I want to get rid of grams of carbon, so it goes on the bottom. Change those grams to moles of carbon. 1 mole is 12.01 grams. And then we said, but a mole is 6.02 times 10 to the 23rd pieces. Grams cancel, moles cancel, I'm left with atoms. I push those buttons. 6.5 divided by 12.01 times 6.02 EE23 gets me 3.3 times 10 to the 23rd atoms of carbon. So I started off with a weight of carbon, ended up with how many there were. That's what we did with it back in chapter 7, I think. We were studying ionic compounds. Okay. So notice what I did. I started off with a weight, ended up with a number. We can count things by weighing them. Make sense? Okay, because we don't want to do the other option. Do you think it's possible to count to 3.3 times 10 to the 23rd? You would not finish your lab in the period allowed if you tried counting as an option. Right? Oh, that works great. I can look up the mole of an element. Just look it up on the table. But most of the things we deal with are compounds. What do I do with a compound? Well, in one water molecule, one H2O, there's 2 hydrogen atoms and 1 oxygen atom, right? So if I had a dozen water molecules, I would have 2 dozen hydrogens and 1 dozen oxygens. If I had 1,000 water molecules, I'd have 2,000 hydrogens, 1,000 oxygens, right? So what if I had a really big number of molecules? Well, if I had a mole of water, a really big number of molecules, there would be 2 moles of H and 1 mole of O. Just like if in a dozen there was 2 dozen H, 1 dozen O. It's just a number. So I'm not going to be able to look up H2O. But I can look up H and O. And then if I figured out how much the H weighed and how much the O weighed and added them together, that would tell me how much H2O weighed. Does that seem reasonable? So to figure out the mass of 1 mole of a compound, and our example is going to be H2O. Determine the moles of elements they have. That would be 2 H's and 1 O. 2 moles of H, 1 mole of O. Find out how much they would weigh. Well, 2 H's times, looking at the periodic table, it says hydrogen's 1.01 grams. And that's 2.02 grams. And the 1O, I looked that up on the periodic table, it's 16.00. And 1 times 16 is 16.00 grams. Everybody okay so far? So all I did was look at the subscripts, look at the periodic table. And then, how much does the whole thing weigh? Well, add them up. 2.02 grams plus 16.00 grams is 18.02 grams. So if I had 18.02 grams of water, that would be a mole of water, which would be 6.02 times 10 to the 23rd molecules of water. So this is the math I need you to be able to do today. Really, really tough. Do a couple of examples, then we'll get that test, and then I'll put the homework up and you can start that too. Okay? So, what's the mass of 1 mole of CH4? I don't know. Well, actually, I do know because I've done it like 3 million times. Okay, I'm not going to find CH4 on the periodic table. But I will find C and H. On the periodic table, carbon's 12.01 grams. Hydrogen's 1.01 grams, but I've got 4 of them because there's a 4 next to hydrogen. So the same way we use subscripts to count how many their atoms were to balance, we need to be able to count how many there are to change to moles. It's the same number. So 12.01 grams from the carbon, 1.01 from the hydrogen, so 4 times 1.01 is 4.04. Hopefully you don't need a calculator for that one. So what does 1 mole of CH4 weigh? Well, 12.01 grams plus 4.04 grams is 16.05 grams. Ta-da. Unbelievably tough? The only way to make it tougher is to give you bigger numbers or more elements, right? And you just do it more times. One last one, just so I make sure. So what is the molar mass of Fe2O3? Iron 3 oxide. Well, I look up Fe on the periodic table. It's 55.85, and I have to worry about 2 of them. So 2 Fe's times 55.85 grams is 111.70 grams. How much O? 3. And I look up that O again. It's still 16.00, like it was last time. 3 times 16 is 48, so 48.00 grams. We always want 2 decimal places. Okay, so every number, just keep those 2 decimal places on these weights. Okay, so what the table gives me, that's what I'm going to keep. And 111.70 plus 48 is 159.70 grams. So that's how much 1 mole of Fe2O3 would weigh. Doable? Okay. I need you to, we're done taking notes then. And I need you to clear your desk. I need a piece of paper, a writing utensil, a piece of paper so you can start the homework if you finish the test. So you can just sit there and twiddle your thumbs for half an hour. Okay. Hey, pass your notebooks backwards. Write down. Oh, and no, you'll take the multiple choice part Monday after school. Okay, is that okay? Yeah, because you're only doing the multiple choice part. Okay. And there's not enough time to take the whole test, but there would be for just the multiple choice part. Yep. Okay, so notebooks backwards. Periodic table like the one you used yesterday. Remember, there's really important stuff on the back side of it. Okay. Should look just like the one from yesterday, except all the questions are different. Okay, same set of skills, though. Not here to surprise you. This is not an evil, nasty version of the test. It's just a different one where everybody's going to remember to identify what kind it is. That's the whole reason why we're doing this. Okay? Questions before we start? You can write your answers right on here, and then I'll put the homework. Actually, there's the homework.